So we think we have an exciting program for you today. We're going to talk about some of the history and the legacy of the two telescopes that are relevant to our discussion. You're going to get a chance to see them today. And a third stop on our tour rotation will be our Visitor Center Museum, where we try to recognize a lot of the science and scientists who've spent their careers working at the observatory. So, first I'm going to introduce my colleague Sterl Phinney, who's going to talk about the 200-inch telescope. So Sterl is a professor of theoretical astrophysics at the California Institute of Technology. He's also an alumnus of the Institute for Advanced Study and an undergraduate degree from Caltech, in addition to a PhD from Cambridge under Martin Rees, who, if you have not met him, is this amazing, remarkable gentleman, really remarkable person, just a prince of a guy. He was the inaugural Saltpeter Lecturer at Cornell University in 1999. He's a winner of the Warner Prize from the AAS in 1995. He was a Sloan Fellow Foundation and a recipient of the Marshall Scholarship. But my favorite part is that it turns out that Sterl is a hidebound clothing traditionalist, particularly when it comes to honoring former directors of the observatory. I do, however, hear that his knees are no longer considered suitable for public viewing. Anyway, with that, we turn it over to Sterl.
For those of you who never met Gary Neugebauer, that was a Gary Neugebauer too. Gary was never seen in long pants. Okay, so I was tasked to tell you about the history of the telescope. You already saw some movies of the construction. In the afternoon, you'll hear much more about Hale. I'll just remark a few things. Just to remind you, Hale, 4 times in his life, built the world's largest telescope. First, the Yerkes 40-inch refractor at the University of Chicago, where he became the chairman of the astronomy department at the age of 24 at the university, which had just opened when he was hired. And the way he got hired was his father agreed to give his personal observatory to the university if they would take his son. But then he had a falling out with the university that this new university he figured should spend 100% of its money on astronomy and not this boring stuff like economics and other things. So he went off and founded his observatory and then built his own university, Caltech, where he could get 100% of the money for astronomy. So then he built the 60-inch at Mount Wilson, funded by Andrew Carnegie, as we'll discuss. The 100-inch at Mount Wilson, completed in 1917. In 1908, Hale had his first spectacular nervous breakdown. He had another one in 1910, and then in 1923, he gave up. He resigned his directorship and went into retirement. And in retirement, he raised the funds for the 200-inch telescope, the Pasadena Civic Center, the Huntington Art Gallery, the National Research Council, National Academy of Sciences, and various other little things when he was too weak to speak to people or do anything. Okay, so here he is surveying Mount Wilson in 1903 with Andrew Carnegie, the steel magnate. And I'll remind you that John D. Rockefeller, who paid for the 200-inch telescope, was the richest man in history. He was worth 2% of the United States at peak. But for 2 years, Andrew Carnegie was richer than Rockefeller, so they hated each other. So, although Carnegie funded Mount Wilson, Rockefeller was damned if he was going to give money to the Carnegie Institution to pay for the 200-inch. So that's why the 200-inch is owned by Caltech and not by the Carnegie Institution. And here's Hale with his 60-foot solar telescope at Mount Wilson, where he discovered solar magnetism. So just to put the little history in context, so the 60-inch and the 100-inch were designed by George W. Ritchie. And after 1917, Ritchie started thinking about bigger things, but Hale and his director, Adams, didn't get along with Ritchie very well, so Hale fired Ritchie. And Ritchie went off to Paris and started designing bigger telescopes than this pathetic little 100-inch telescope. The next year, this timber merchant from Colorado, Bill Weber, visited the 100-inch, was very impressed, began writing to Hale and Pease, who was the new instrument designer, about how big you could make a telescope and wouldn't it be interesting to build something bigger. So Pease made some drawings, which I'll show you in a minute, for a 300-inch telescope, which he felt was sort of the largest that you could conceivably make. Hale heard in 1926 that Ritchie was actually successfully starting to raise money in Paris for a bigger telescope, so he authorized Pease to rush out a paper describing his earlier work on the 300-inch. Then, as we'll discuss, the Rockefeller Foundation came by in 1926. And also in 26, Scientific American made a sort of popular version of this PASP article. And when Hale showed all this to the Rockefeller Foundation when they visited in 1926. So here's Pease's drawing for the 300-inch telescope. That's 7.5 meters. Those are given metric units. You'll see that the mounting is a little different than the current mounting. And we'll get to why that is in a little bit. So in April 1928, Hale had heard rumblings that maybe the Rockefeller Foundation was actually interested in building a bigger telescope. So he wrote this article for Harvard Magazine. I don't know if you can see it here. It says, The Possibilities of a Large Telescope by George Ellery Hale. The article's in the magazine. So after this was printed, he hot off the press, he rushed a copy of this nice article in Harper's to the Rockefeller Foundation. Notice April 1928 published. October 1928, $6 million, that's roughly $200 million today, grant to Caltech for construction of the 200-inch telescope is approved. Foundations moved fast in those days. So there was a little bit of an issue that this $6 million was to build the telescope. There was no money to operate the telescope. But the Caltech trustee, Henry M. Robertson, agreed to fund the building for astrophysics, which you can still see on campuses in Robinson, the astrophysics building, now run for geology, and to endow the operations of the observatory. And fun fact, Henry M. Robinson was the lawyer who organized the merger of U.S. Steel when Carnegie sold out to Morgan. And as the merger in charge, he took his 10% or something, and so he retired at the age of 39. Where retired meant that he was the chair of he was the owner of several banks, the Newport News Shipbuilding Corporation, advisor to Standard Oil, and all sorts of other things in his retirement. But he also endowed a lot of stuff about that and operation of the 200-acre. And then one very important thing, in November 1928, George Ellery Hale heard about this amateur astronomer who formerly was a polar explorer who'd had all kinds of exciting adventures in Antarctica. But he was an amateur astronomer, and he had invented this split ring mount, which allowed yoke-like telescopes to point everywhere in the sky, but be much more stable than this thing. And he was also an architect and a brilliant draftsman and a brilliant mirror builder and telescope designer and telescope builder. So Hale hired him. And then in 1929, Hale wrote another Harper's article called Building the 200-Inch Telescope, because they had decided that 300 inches was maybe a little big. That was going to be like 30 million, but 200 inches they figured they could do, and 6 million was sort of more what Rockefeller was interested in giving. So it became a 200-inch telescope, and it now has the familiar split ring mount, which you can see here, which was Robert W. Porter had actually patented in 1921. Here is a picture, actually, of Edwin Hubble and Richard Chase Coleman, the famous professor of relativity at Caltech, with a model of the 200-inch taken in 1931, which you notice that the mount is not the mount that was already approved in 1929. So they clearly hadn't updated the model. Now, you'll notice in 1928, if you know about U.S. history, was a great year to get $600 million. 1929 was a great year to start hiring people to build stuff because the economy had collapsed. And I guess they had not invested the $6 million in something which was worthless. So there was a Great Depression. There were lots of people eager to work. Throughout 1930, they tried to make a fused quartz mirror, which many modern telescopes use, but those completely failed, so they selected Pyrex or silicate glass instead, and the contract was let to Corning Glass Works in New York. During that time, Russell Porter built 12 telescopes. They site tested all over California, and where we're sitting today, one, Palomar was selected as the best site. Same Russell W. Porter, I mentioned he was an architect as well as a telescope builder, so he actually designed the Robinson Astrophysics building at Caltech, and the Caltech machine shop, and the Caltech optical shop, and by the way, the Griffith Observatory, in the Case Western Observatory, and all kinds of observatories all over the U.S. In 1932, John Strong, who I had the great pleasure of actually meeting late in his life when I was in high school and being able to play in his lab, he invented the idea of vacuum coating mirrors and realized that you didn't have to use silver anymore, which tarnished very quickly, but you could coat them in aluminum, which reflected much better in the blue and also didn't tarnish so fast. And so it was decided that in fact this new mirror would be aluminum vacuum coated, and that actually the same Russell W. Porter built the first vacuum system for doing John Strong's experiments. The same Russell W. Porter decided where all the telescopes were going to be here. He decided where the 18-inch, 48, and 200-inch would be, and he designed the buildings that you'll see. So it's a beautiful cathedral that the 200 inches in is, again, Russell W. Porter. Okay, so in this article, when we get to the science, Hale argued that the reasons for needing a telescope bigger than the 100-inch, the 200-inch will see things 4 times fainter and the same exposure time. And he argued that that was needed to study the evolution of stars, the evolution of galaxies, and dense matter in the newly discovered white dwarfs. In 1927, also a very famous Caltech professor, Ira Bowen, who became the first director of Palomar, understood both resonance fluorescence and the nature of forbidden lines in astrophysics, which had been thought were nebulae or some exotic element that didn't exist on the Earth. But he showed that using quantum mechanics, you could show they were just transitions between energy levels which didn't happen at the high densities you could make in laboratory vacuums that did happen in interstellar space. So Hubble called that out as another way of sort of testing quantum mechanics of the universe and exciting things to do with the big telescope. Okay, so the construction, I already mentioned it was a Rockefeller gift, so it was not going to the Carnegie Institution in Pasadena, which was operating the Wilson telescope. Okay. All of the apparatus, the 10-ton gears to tiny little 50 parts, were manufactured in the instrument shop at Caltech, except during 1942 to 1945. Of course, they were building torpedoes and rockets and things there. And the mirror was polished in the optical shop at Caltech, which is now you can go see. It's the synchrotron building, number 49 on the Caltech campus. And I'd just like to point out that, again, this was designed by Russell W. Porter, and one of the subtle things is the mirrors have to be polished to exquisitely accurate surfaces. If the temperature changes, the mirror expands and contracts a little bit, so you don't actually, if the temperature changes between the morning and the afternoon, and you measure in the afternoon and you grind in the morning, you're testing and designing the wrong figures, so you want to keep the temperature absolutely constant. So this building actually has 6 inches of cork embedded in the walls to insulate it. It also has an air conditioner, and I'll just remind you that Carrier invented the compressor air conditioner in 1922, built the first model demonstrated in 1925, and Porter already had designed a building to have one in the 1930s and installed it in 1931. So air conditioning was probably one of the first large buildings other than a cinema to actually be air conditioned. Then the 18-inch Schmidt and the 48-inch Schmidt telescopes here had their optics and mechanics also constructed on campus. Some of you, probably many of you know the story of the 200-inch glass blank. Corning poured it in February 1934. The mirror is not a solid piece, but to make it lighter, it has pieces that were molded loose to make sort of essentially holes in the back of the mirror to support it and lighten its weight without reducing its strength much. The pieces of the mold broke loose, they melted basically in the heat of the molten glass and ruined the mirror, so that mirror is still, you can see it in Corning, New York. The second one was poured in 1934, but to cool a glass blank of that size without having it shatter on cooling, like taking pots out of your oven and putting them under cold water, they break. If you cool this too quickly, it would break, so they had to cool it down over 10 months. It took 10 months to cool down. But unfortunately, after 7 months, the river that runs by the Corning Glassworks flooded the whole ground floor, shut off the electricity, which was keeping the mirror slowly heating it and letting the temperature drop. So for 3 days, the mirror cooled without any heating control until the heroic workers at Corning managed to dam off enough and get the electricity running again, and the mirror was okay. Then, as I'll show you, it had an exciting train trip across the United States for 2 weeks. It was ground and polished at Caltech from 1936 to 1942. Wasn't quite finished then, but then all the opticians were needed to make bomb sights and rangefinders, cameras for bombers and things like that. So the polishing didn't restart until 1945. At the end of 1945, it was completed, at least the Caltech part was completed on October 3rd, 1947. And a month and a half later, at 3:38 a.m., the now I think then it was called the State Highway Patrol, and now it's the CHP, California Highway Patrol, in shoring up a lot of bridges. The mirror began its trip to Palomar. So here's the mirror in Corning, New York, being loaded onto a flatbed for taking to the train station, or maybe I'm not sure, that might be a train car actually. You can see there was a good crowd coming to watch. Notice the cars. Okay, this was a little while ago. Notice also that most of the gentlemen in the picture, I don't think there's anybody here with a hat. Almost all of them with a hat. I thought it was fun. Okay, here it is. IREX Corning mirror on the train. Notice the trains are a little different now. I think this is probably near the end of its journey, judging from this image. As you see, it's kind of a tight fit under a lot of railway bridges, so there were some stops and checks to make sure that the inch that they had measured was actually an inch in the right directions. Well, I guess past that one. Here's the Pasadena Star News, April 10th, so it arrived on Easter morning in 1936. Huge crowds came out to see the telescope arrive, which was blank, and arrive in Pasadena. Giant Eye arrives in Pasadena. Small weeks mirror watch unloading. Santa Fe worker and Savant sleeper. Okay, so here it is at the Caltech optical shop, front building, and you can get a sense of the size of the mirror now. And here are a bunch of images of the various stages of polishing in the Caltech optical shop in Pasadena. The construction. So here's the optical shop today. I just thought I'd show you. It's still there. It still is full of stuff under construction. So after the 200-inch mirror left, remember it left in 1947, in 1950, Caltech installed what was then the world's highest energy synchrotron, the GGB synchrotron, which I think held the title for like 2 years or something. And then after that was closed in 1970, the 7 10-meter telescopes, twice the size of the Hale, but for millimeter and sub-millimeter, were built in there. Then several balloon payloads for studying gamma ray and X-ray astronomy. Microwave background telescopes, BICEP, Echo-ray. You'll notice in here, I think again another LIGO vacuum system. The LIGO vacuum systems were assembled there. Instruments for the Keck telescopes and Foxfire and KCWI. So Porter's building is still at the forefront of astrophysics. So here's Russell W. Porter, I mentioned. So he was hired in 1928. Remember that in 1937, the telescope hadn't been built. The mirror had just arrived at Caltech. Porter made these amazing series of drawings that you can see copies of throughout the Cahill building on the Caltech campus in 1937, showing all the features and the observing and all the little mechanisms and everything exactly as they were constructed 10 years later. So they're really amazing drawings. And they're not really blueprints, but they're more useful than blueprints in a sense because they actually show you how the stuff is going to work in a three-dimensional Okay, so another thing that happened, in 1935, the project manager for decided that this split yoke and all these little mechanisms and the electronic control systems were so complicated that he wasn't going to build the real one unless he had a model to test it all on. And so this is a 1/10 scale model with 20-inch telescope instead of a 200-inch telescope, which has all the little limit switches and electrical mechanisms of the real 200-inch and mirror and everything. There's no room for a human inside the prime focus gauge on the model, but other than that, it's just like the real thing. And this was mounted on the roof of the Robinson Astrophysics building in Caltech. And when I was an undergraduate, probably when Tom Sofer was an undergraduate in AY20, we had to go up and measure the separation of double stars with a field micrometer looking through this thing, which tracked terribly and was very hard to point. And it was a pretty miserable telescope. Anyway, it's now in Corning, New York. Corning traded Caltech 14-inch Celestron for this. They refurbished it. It's still used for public observing. You can go see it in Corning, New York. So here's 1937. You see the 48-inch Schmidt dome was all finished, and the 200-inch dome is under construction. The mouthpieces are being put together in 1938. And of course, I mentioned work stopped in World War II in 1942. The mirror was taken to Palomar. The finished mirror was taken to Palomar in 1947, but there were problems with the mirror support. That there's complicated mechanisms. As the telescope tilts, you have to change the pressure on the back. So there was a complicated mechanical design, and it didn't work very well. So it was rebuilt and new insulation put around the edges to change, improve the figure changes between day and night. Those were installed in fall of 1948. Now remember, the dedication you just saw was in June of 1948. So like many dedications, it was sort of working, but not really done. The mirror didn't actually have any aluminum on it, so you could look at bright stars, but not at faint stars. So the mirror figuring continued until September 1949. It was had its first coat of aluminum in October 49, and observing began in November 1949. So 16 months after the dedication. In 1948, Jesse Greenstein arrived at Caltech and founded Caltech's astronomy department. So the first graduate students who were advised by Walter Bottom, not by Jesse, were Chip Hart and Alan Sandage, who figure probably is what comes. Here's the mirror going up the mountain to Palomar. So for the range, I want to talk about the legacy of the 200-inch telescope. And it's maybe difficult for any of us to imagine how important this was to the United States. This was just after the war, things are recovering, and here was this great icon, been under construction for 20 years, biggest telescope in the world, going to revolutionize astronomy. And so it became, it got its postage stamp. United States Steel said only steel can do so many jobs well, so advertising steel. Deepskin, I know. Does anybody else know what Deepskin made? Slide rules and drafting equipment. Okay, so mighty Palomar, signet of engineers, buy Deepskin slide rules, and you too can design. Diamond T trucks, it says down here, transport the oil for the lubrication of the 200-inch horseshoe. So buy Diamond T trucks. Standard Oil, of course, well, they supply the oil. And this is Wright aircraft engines, telescoping time. Shorten your journey just as looking through the telescope. So, modern miracles, 200-inch telescope and bond homogenized bridge. Okay. Now, this one, Wonders of America, world's largest telescope. And so this is an advertisement for Prince Albert pipe tobacco, which burns 86 degrees cooler than any other brand of pipe tobacco. So they're explaining how it could be really cool if they're using the telescope with the smoke Prince Albert pipe tobacco. And this is an advertisement for Viceroy cigarettes. Now, I'd just like to point out that one of these is really appropriate, and the other one is completely false advertising. Okay, so here's Edwin Hubble, who all of his pictures has a pipe in his out. So it's appropriate to advertise Prince Albert right to that. But this picture, you'll notice the similarity to this one. Okay, they copied this artist's impression of Edmund Hubble pretending to guide the 48-inch Schmidt. But notice that he has a pipe in his mouth. And notice that the pipe has been painted out for the cigarette air. So, false advertising. Okay, so enough for the humorous legacy. The real legacy. So before the 200-inch telescope, the Earth was a place of change, turmoil, corruption, and the heavens were perfect, eternal stars. Nothing changed. In the 1500s, there had occasionally new stars, but they might be atmospheric phenomena like comets, and therefore didn't really ruin this idea. And of course, before the 200-inch telescope, there were hints, but really our modern conception of the universe really started with the 200-inch telescope. That stars evolved with time, galaxies evolve and change with time, the universe changes with time, stars create the elements that we're made of in their nuclei. The young universe was very different than the one we live in today. There were quasars and radio galaxies that were thousands of times more numerous than they are today. And you might think that how could a 70-year-old telescope still be contributing to astrophysics? But every few years, there's revolutionary new detectors, new instruments put at the front. So when it was designed, it was envisaged that everybody would take pictures, photographic plates for the spectra and the images. But when it was actually built, a lot of the time was immediately used for photoelectric photometry because it was 10 times more accurate than trying to say, well, that's a big dot on the plate and that's a little one, so this one must be brighter than that one. Photoelectric photometry, you could measure the voltage and figure out how bright the star was. Then in 1965, there were infrared detectors put on the telescope. It was actually the world's largest millimeter and submillimeter telescope from 1973 to 1983 before larger ones like 10 meters were actually built. So it was used as a millimeter and submillimeter telescope. Photon counting detectors with high quantum efficiency, so about 100 times higher quantum efficiency. Photographic plates were started to be used in 1973. The first demonstrations of closure phase interferometry, speckle interferometry in 1988. First astronomical CCDs were put on the telescope in 1977, a whole 120 by 160 pixels, 10 kilobytes, 10 kilopixels, not megapixels, not gigapixels like we have now, kilopixels. Vector vortex coronagraph installed in 2009, in 2014 there's a high-speed electromagnetic CCD imagers can take 1,000 frames a second installed. So it's a different telescope than it was in 1970. Same mirror, same mount, totally different detectors. Okay, so let me just see how much time do I have left?
That's 10 minutes.
10 minutes, okay. So I'll just sort of go through a few things. So one of the first things that the Hale telescope did was to triple the size of the universe. So it doubled the distance to Andromeda, made the universe roughly 4 times larger by changing the Hubble constant, so I sort of averaged it and calling it tripling. Factors of several. And so the issue was that one of the ways to measure distances to stars is to use the Henrietta Leavitt's period luminosity relationship for variable Cepheid stars, that large stars vary slowly and are bright, small stars vary quickly and are faint. And so if you measure the period of the variability of a star, you can figure out how far away it was, or it is. But originally everybody thought that there was just one relationship for them. But Walter Baade and Henrietta Swope, his assistant, who also helped with funding because her daddy was the president of General Electric Corporation, realized that in fact there were 2 different kinds of Cepheid variables of these variables, so-called RR Lyraes that were formed that you saw in old systems like globular clusters, and the Cepheid variables that you saw in young clusters of stars. And one of the first things that happened was when Baade took images of M31, the Andromeda galaxy, with the 200-inch telescope, he was expecting, at the distance accepted then, to see lots of RR Lyraes and globular clusters and halo of this galaxy, and he didn't find any. So he immediately knew that Andromeda must be farther away than everybody had thought. And after they found some giant stars and gifts in those regions, they decided the distance from 31 must be twice as large, and they then extended to more distant galaxies and showed that Hubble's value for the Hubble constant had been wrong by about a factor of 5, and so the size of the distant universe increased enormously. Unfortunately, the age of the universe also increased because there was a problem with Hubble's value that the universe was younger than the Earth and the rocks. So that fixed that problem. So Burbage, Fowler, and Hoyle in 1956 wrote this amazing paper where they predicted much of modern understanding of how nuclear reactions in stars create the elements. So Jesse Greenstein immediately said, "Well, that's just theorists," went to the airport and said, "We're going to measure the stellar abundances and check these theorists." And the Air Force said yes and gave him money to hire postdocs and graduate students for the next 13 years, so that was a very good thing. So a lot of the 200-inch line was then in support of this so-called abundance project at Caltech. They showed that stars and globular clusters had very weak absorption lines, meaning that many of their elements were much less abundant than in the sun by a factor of about 100. And just so you appreciate, in those days, to get a high-resolution spectrum of a giant star in a globular cluster, you might need to expose for 3 nights. So you sat up there overnight, guiding the telescope, you closed the shutter, went to sleep in the day, went back, carefully pointed the telescope in the same place, opened the shutter, guided for another night, went back, waited for the bad weather, went back 2 nights later, opened the shutter, all on the same piece of photographic plate. 3-night exposure. Greenstein, Wallerstein, Walsargen, and Mosgard company showed that these stars with very weak abundances of iron could actually have normal amounts of magnesium and calcium, just like the amounts in the sun. And that meant that the way that these elements were being produced, they weren't all just being produced in one kind of explosion, but there had to be 2 kinds of explosion. One that produced these elements and one that produced those elements, and some stars got more of this and some got more of that. And that basically is the beginning of our whole idea of how the chemical evolution of galaxies and the spectrum matter in the universe happened. Chip Arp showed that originally the idea was that young stars had lots of metals and old stars didn't have very much. That's obviously the equation for explosions. And the young stars should have more metals in the old stars, but Arp showed that there were very old stars near the center of the galaxy that had much higher iron abundances than the sun, even though they were just as old as the globular cluster stars. So the abundances depended on where you were, not just the age. So that's the beginning of our current idea. The galaxies form in the middle, and then stuff grows around them. So one of the great things that the 200-inch work really did was basically our whole modern theory of stellar evolution was this interplay between the observers at the 200-inch and the theorists like Fred Hoyle and the Burbages, Martin Schwarzschild from Princeton and others, working very hard to understand the connection between the observations and the data. So this is a very young cluster, where young in astronomy means like 2 million years old, sort of still in diapers, basically. And you notice that there are some red stars that are bright, and there's some blue stars that are bright. And then there are a whole bunch of fingers or white stars in here. If we go to sort of adolescent and middle-aged clusters, 10, 100 million, 5 billion years old, you can see this one has lots of blue stars, no red stars. This one has blue and red stars. And here's an old globular cluster. You see there are bright red stars, slightly less bright blue stars, and then a whole bunch of white stars in it. So one of the, this is an image of the center of a globular cluster from Hubble Space Telescope. And I'll play this as a movie, but you notice that there are red stars, which are bright, there are orange stars, which are less bright, some blue stars that are pretty bright, and a whole bunch of white stars in the back. So one of the things that astronomers do is the color of the star tells you its temperature, and the brightness of the star tells you how big the star is, times the temperature to the 4th power. the first thing to do is separate the stars by temperature. So I'll put blue stars on one side and sort of do bright pink, red, orange, yellow, green, blue. And then we'll sort them, we'll put the bright ones at the top and the faint ones at the bottom. So this is what's called the Hertzsprung-Russell diagram. You'll see a lot of these. Okay, so here's an example of one of those without the pretty colors in it. So this was work by Alan Sandage in 1956, carefully doing that for lots of different clusters. So here's H Pi Persei, the first one I showed you, the young baby one. And you see they're bright blue stars, they're also bright red stars. And in the Pleiades, there's bright blue ones, but there are no red ones. And in M67, there were blue ones and red ones over here. So the interpretation which Hoyle and Schwarzschild and others came to is basically stars burn hydrogen along this line. But when they run, and what varies along this line is the mass. So these are very low mass stars, these are very massive stars. And as they fuse hydrogen in the center, then as they run out, they begin to evolve towards the red, and that was understood theoretically by Schwarzschild and then demonstrated by Sandage and others. And people had originally thought that these red stars were young stars that were just forming, but these observations with the modeling showed that in fact they were very old stars, and what had been missed was the idea of convection in the center. Okay, so Arp and Sandage used photoelectric photometry to produce these beautiful diagrams, which are basically, these were the textbook diagrams of stellar evolution for 40 years. Every textbook had these two images in them as the example of how stars evolved, how HR diagrams look like. The endpoint of stellar evolution, of course, after the stars run out of nuclear fuel, are white dwarfs. So Jesse Greenstein and his graduate student Virginia Trimble measured the gravitational redshifts of 20 white dwarfs and measured their masses so that one could figure out how massive the cores of the stellar evolution were. Greenstein sort of got spectra of about 600 white dwarfs and showed there were huge variations in the surface compositions, measured the rotation rate. So basically the whole field of white dwarf research is basically Jesse for 30 years. One thing I just like to highlight, so Roger Griffin and Jim Gunn, Griffin and Gunn here standing in front of the 200-inch telescope. So the old way of measuring the radial velocities of stars to measure the redshift is you would look for a spectral line and you would measure how much it was shifted, and then you would use that to determine the radial velocity. But Griffin had the brilliant idea that instead of doing that one spectral line at a time, why not just do the whole spectrum at once and just shift the template spectrum back and forth until you get a good match, and then you can just read off the velocity in a few seconds instead of taking 6 months of graduate student time carefully measuring on photographic length. And you could do, by the way, you could also do it about 30 times more accurately than the graduate students measuring. So they did this, they measured the velocities of stars in lots of clusters, so they discovered 60 spectroscopic binaries in the Hyades, which is the nearest star cluster, and using the relative motions, how fast the stars are going around each other from Kepler's laws, you can determine the masses of the stars. And one of the things we'd like to know is that in this diagram, I told you that there were less massive stars here and more massive stars up there. How do we know that? Because Gunn and Griffin measured their masses with the spectroscopic binaries and showed that there's a mass-luminosity relation. Low mass binaries had low luminosity and high mass ones had high luminosity. So that's how we know how fast luminous stars and different masses are. They did another thing is you can think of these globular clusters as groups of a million stars, which are basically like a gas. In the gas, the heavy molecules move more slowly, so the heavy stars should move more slowly. So they should sit in the middle of the cluster. They can't get up the hill to the outside. And they showed that in fact that happened. Identification of radio galaxies. So here's Sir Martin Ryle with the Cambridge Radio Array. And when they found these radio stars, who do you call to figure out what they are? You call Vladimir Minkowski at the 200-inch. And they identified them. So RSA is the Crab Nebula, remnant of the supernova. Virgo A was this nearby galaxy with this funny little jet sticking out of it. Cygnus A was this weird pair of galaxies colliding with each other. It was very faint and very distant. Hercules A was 650 megaparsecs away, and they very rapidly got out to sort of 3,000 megaparsecs, redshift and a half. So suddenly these weird little faint radio things that were objects which were not stars, but were at the edge of the universe, that were actually the brightest things in the whole sky in the radio. So that was really stunning. So in these highlights, I've sort of been talking about discoveries. So you might think, oh, discovering radio galaxies was the big thing that Palomar did. But when you discover some new species, discovering it is very nice. But most of the work is actually figuring what it eats, where it lives, where it sleeps, how it reproduces, how it raises its children, what kind of food it eats, what kind of vegetables it eats, all that sort of thing. And that takes a lot more work than looking and say, oh, there's a new kind of bird. So this was finding the new kind of bird. Then there was 30 years of work to figure out how many of these are, how bright they are, how do they evolve with cosmic climb, where do they live, how do they get their gas, and so on. So that was 30 years of work, again, mostly the 200-inch. So here's evolution of the LAC objects found by the Fermi gamma ray satellite in 2014. There was, I guess, similar things for X-ray selected radio source. So I mentioned the Crab Nebula. So this radio source in Taurus was identified as the remnant of the supernova of 1054 AD. In 1953, Shklovsky had written a paper saying that he thought the radio emission and maybe the optical might be this new radiation which had just been discovered in synchrotrons. Remember the Caltech synchrotron in 1950. So the electrons go around, they produce this weird glow, and he realized that it was because they were being accelerated in the magnetic fields, and he thought that maybe this could happen in the universe too, not just in synchrotrons. The characteristic of that radiation is that unlike all other kinds of radiation, it's highly polarized, like 50% polarized. So Vada went off and took pictures of the Crab Nebula through Polaroid filters pointed in these different directions. And you can see that the nebula looks totally different depending on which way you put the Polaroid filter, which immediately tells you that it's very highly polarized and yes, it was synchrotron radiation. Then you remember that Virgo A, that funny radio galaxy with this funny little optical jet sticking out? Well, of course, Vada took pictures of a few polarizations there, and yup, that one's polarized too, so it's optical synchrotron radiation in the radio galaxy. So, another discovery at 200 inch. And then, of course, the thing the 200 inches may be most famous for is Martin Schmidt, here with Jan Moore, the great Dutch astronomer, sent him over to Caltech for finishing, but then Vada kept him. From the 200 inch, they discovered quasars, so there were these mysterious radio sources which looked like stars. This one you might notice is a little funny, that little jet pointing out of it in the optical. But the spectral lines didn't make any sense. Maybe they were technetium or californium or something, but no, Schmidt realized they were actually hydrogen, just redshifted much more than anybody had ever imagined, certainly a star could ever be. And the redshift quickly got up to 0.3, 1, 2, 3, now 7. So the spectra are enormous. These objects are very far away. They're tiny. They vary in a year, so they're less than a light year across. So their size is like 1/30,000th the size of a galaxy, but they're 100 times brighter than a galaxy. So it was quickly realized they couldn't be powered by nuclear fusion in stars. Willie Fowler thought they could. Feynman showed him that such stars would collapse. And Saltpeter and Zelgovich and Novikov in 1964 independently realized that they had to be feeding black holes. And by the way, you get black holes that sort of been invented the year before. So just in time to explain quasars. As I mentioned, again, lots of study of the evolution. The thing to notice here is this is the log of the number density of quasars. There's 2.5 and 3. So quasars with redshift 2.5 were 300 times more common in the universe than they are today. So that was the end of the steady state theory of the universe. The universe in the past is very different from the universe today. So, just like to highlight Beatrice Tinsley, who I had the great pleasure of meeting very late in her life. We actually had the same birthday. So she was truly an amazingly brilliant person. So she had the idea that stars evolve, galaxies are made of stars. So we can figure out if we take a spectrum of a galaxy, we should just be able to add up the spectra of a lot of stars until we get a match and figure out what kind of stars are in the galaxy, how old the stars of different ages, how many stars of different ages there are, and therefore say how the galaxies assembled as stars as a function of cosmic time. And by the way, that meant when you look back in the past, the galaxies would have different, even if they had all formed as stars very early, because the stars are evolving, the galaxy's brightness would be evolving. And people had missed that before, and they're based trying to measure the cosmic parameters. It's rather remarkable that in 1975, Gunnar Oak wrote a paper measuring the brightnesses of galaxies out to high redshifts and determining the shape of the universe. But they didn't include this. So in 1976, Tinsley and Gunn put in the evolutionary corrections and inferred that the universe was accelerating due to a positive cosmological constant in 1975. Probably most of you heard about this in 1998, which was the time the Nobel Prize was given for it, but Tinsley and Gunn got it right in 1975. And finally, the thing that first got me sort of really excited in being a theoretical astrophysicist was looking at pictures like this, really cool pictures of these galaxies doing stuff with each other. And then our Toomri, shortly before I got interested in this, also looked at them, but they were older and had bigger computers in 1972. So they had the idea of just solving Newton's laws of motion for a bunch of stars and two galaxies and running the two galaxies together. And they showed that if you solved Newton's laws and ran two disk galaxies together, you can make something that looks like a lot like this. And if you did a slightly different one and looked at it from this direction, you could see something that looked a lot like that one. And so that was how we knew the galaxies actually are not island universes that never touch each other, they're smashing into each other all the time. And indeed, they can produce amazing things. So here's an ARP 1966 image of this weird ring galaxy. Here's a modern Hubble plus Chandra image of it. And same Toomri and Lin showed that if you drop one galaxy through another one, you can make beautiful rings, and that's how the rings get made. So this galaxy probably went through that one and turned each other into rings. And I mentioned black holes and quasars, but one of the first dynamical evidence for black holes and galaxies was Peter Young, who tragically committed suicide, I guess, 3 years after this, and Walt Sargent, using Alex Boxenberg's photon counting system that I mentioned early on, took spectra of M87, that's that same big galaxy with the jet sticking out of it, and they showed that as you went towards the center of the galaxy, the spectral lines of the stars got broader, and that meant they were moving faster, and they were moving so faster that there must be a 5 million solar mass black hole in the center, and we still think that's true. Okay, quasar absorption lines, discovering of the intervening gas filling the universe was another great thing that they did. Infrared universe, seeing the universe in infrared light. Sorry, Todd, this is one of the heroes here. I need to put his picture up so you can wave it on. First map of the center of the galaxy in the infrared by Becklin and Neugebauer in 1968. Then finally, in 2010, the spectral vortex spectrograph with the images and the first spectra of extrasolar planets. So it's still doing great stuff.
Thank you very much. Awesome. Thank you very much, Cyril.